Welcome back. If you're ready to see how shrinking a completely ordinary material down to the nanoscale fundamentally alters reality, well, you're in the right place. Today, we're taking a deep dive, an explainer really, into the physics of the unimaginably small. You know, at the macroscopic level, we're totally used to materials having fixed properties. A block of gold is golden, right? But when you crush materials down to just a few nanometers, those familiar rules of physics, they completely break down, and a whole new kind of magic takes over.
I want you to burn this concept into your brain right now. Size controls electrons, electrons control light, and light creates color. This right here is the absolute foundational rule of nanomaterials. It's the recurring motif for our entire journey today. Literally everything we look at from this point forward traces back to this one beautiful sequence of cause and effect.
Okay, let's dive into this. Here's our roadmap. We're going to literally watch a material grow. We'll start from a single, isolated atom way over on the left, to small clusters, then into precisely engineered quantum dots and nanoparticles, all the way back to a massive, clumpy bulk material on the right. This whole progression proves that size isn't just about, how big something is. At the nanoscale, size is actually a brand new control parameter.
To keep things super structured, here's our map for today. First, the magic of size. Then, ions and nanoclusters, quantum dots, plasmonic nanoparticles, the return to bulk, and finally, the power of light.
Section 1. The magic of size. Why shrinking changes all. What's really interesting about this slide is how it summarizes our entire journey at a single glance. Notice how at every single scale threshold, the dominant physics completely changes. Moving from the angstrom scale down to nanoclusters, into the 2 to 10 nanometer range of quantum dots, and then the 10 to 100 nanometer range of plasmonic nanoparticles, the behavior of the electrons fundamentally shifts at every stop. And because that electron behavior shifts, the optical properties, the stuff we can actually see with our own eyes, shift right along with them.
Section 2. Ions and nanoclusters. Angstrom to 2 nanometer scale. So, before a nanoparticle even exists, our starting point is just a simple metal salt dissolved in a solution, isolated gold ions. These are tiny, charged species no larger than a single atom, measuring about 1 angstrom. At this stage, electrons are tightly, and I mean absolutely tightly bound to individual atoms. There's no visible color, no fluorescence, and honestly, no magic happening just yet. It's really just basic chemistry. Size doesn't even have a real meaning here, because we're basically just dealing with dissolved ions. But watch what happens when we add a reducing agent, and those gold atoms finally start joining together. They form what we call nanoclusters. These are groups of a few, up to maybe a few thousand atoms, sitting right in that 1 to 2 nanometer sweet spot. They're too big to be single atoms, but way too small to act like bulk metal. In this bizarre intermediate world, molecular-like states with discrete quantum levels actually begin to form. And, for the very first time, we get to see the faint whispers of weak fluorescence. Section 3. Quantum dots. Trapped in a tiny box. As these particles grow into that 2 to 10 nanometer range, a seriously profound physical effect takes over. It's called quantum confinement. Now, in a normal bulk material, electrons just roam freely through what is essentially an infinite space. But in a quantum dot, the particle is so unimaginably tiny that the electron is literally physically trapped. It's confined. It's exactly like a particle trapped inside a microscopic box. And because of this intense restriction, the energy levels stop being a continuous band and they become discrete and quantized. To really wrap your head around this, lean into this analogy. Think of a violin string versus a thick guitar string. If you have a smaller, tighter string, it produces a higher frequency, right? Well, the exact same applies to our trapped electrons. If you have a smaller particle, it creates a larger energy gap, which requires a higher energy photon resulting in a short wavelength blue emission. But if you have a slightly larger particle, the energy gap is smaller, the photon has lower energy, and it emits a longer wavelength red color. And this brilliantly illustrates that exact concept in the real world. By doing absolutely nothing more than controlling the synthesis time and temperature,
Literally just changing the physical size of the particle, chemists can tune the emission color of quantum dots across the entire visible spectrum. From the small blue dots on the left to the larger red dots on the right, it is the exact same material. They're just different sizes acting as differently tuned boxes for our trapped electrons. Crazy, right?
Let's reiterate the master equation of the nanoscale right here, just to be sure we've got it. Smaller particles give you that larger change in energy, giving you a high-energy blue response. Larger particles give you a smaller change in energy, resulting in a low-energy red response. Size dictates the energy gap, and that gap dictates the light emitted.
Section 4. Plasmonic nanoparticles. Collective oscillation.
Okay, so beyond 10 nanometers, the quantum box just gets too big. The electrons are no longer quantum confined. Instead, they start moving collectively, altogether. This creates a phenomenon called Localized Surface Plasmon Resonance, or LSPR. Let's break this down step by step so the physics doesn't feel overwhelming. Imagine incoming light acting as an electric field. It pushes the free electrons in the metal to one side of the particle. But then, the positively charged metal lattice pulls them right back. The electrons overshoot, creating an oscillation. It's exactly like a pendulum or water sloshing back and forth in a bathtub, moving perfectly in sync with the light.
And because of this collective electron sloshing, the optical properties are just absolutely stunning. When light strikes a 10 to 20 nanometer gold particle, the LSPR effect causes it to absorb green light. And since green is absorbed, what gets reflected back to our eyes is a vivid ruby red color. Think about that for a second. It is solid gold, but because of its nanoscale size and the way its electrons oscillate, it looks like deep red fruit juice instead of traditional shiny golden metal.
Section 5. The return to bulk, when nanoscale ends.
Take a look at this stark visual contrast. On the left side, we have our vibrant, ruby-red plasmonic nanoparticles. But on the right, you can see what happens when those particles clump together and finally exceed 100 nanometers. They just turn into dull gray or black liquids. As they grow into these massive aggregates, the nanoscale magic literally vanishes right before our eyes.
When we hit the bulk scale, all those special properties disappear. Quantum confinement is totally gone. The sharp LSPR band broadens and dampens. The vivid color is lost, the surface area drops, and the particles just settle out of suspension. But here is a pretty surprising fact for you. We actually exploit this loss. When gold nanoparticles aggregate in the presence of a target molecule, like a specific virus, their color visibly shifts from red to blue. We intentionally use this controlled clumping to create rapid, naked-eye pathogen biosensors. So even the loss of nanoscale magic is incredibly useful.
Section 6. The power of light. Real-world applications.
So the crucial point is that by understanding this journey of size, we can engineer some truly incredible innovations. At the nanocluster scale, we build fluorescent labels. At the 2 to 10 nanometer scale, those tunable quantum dots, they're powering your high-end LED displays and cutting-edge bioimaging. And at the 10 to 100 nanometer scale, plasmonic nanoparticles are being used for targeted photothermal therapies to fight diseases. Every single size regime unlocks a distinct, world-changing application.
Let's hammer home our recurring motif one last time, because it really all comes back to this. Size controls electrons, electrons control light, and light creates color. By mastering this simple yet profoundly powerful progression, scientists hold the key to designing nanomaterials with precisely tailored optical, electronic, and biological properties.
We've zoomed from invisible ions to glowing quantum dots through ruby-red plasmonic metals and all the way back to bulk materials, proving that altering scale actually alters reality itself. The rules of physics at the macroscopic level are just the tip of the iceberg, right? So armed with this knowledge, how will you use size as a new control parameter to engineer the future? Keep questioning, keep exploring, and we'll see you in the next explainer.